This is geometry lesson 13.3, geometric means in right triangles. So the big idea here says that the altitude to the hypotenuse of a right triangle creates two triangles similar to the original, from which relationships between the lengths of their sides can be derived. So we're going to relate this directly to right triangles that have an altitude drawn to the hypotenuse and how that creates three similar triangles. That's how this fits into this unit. But what's special about that is the relationship that it creates between some of those segments. And we're going to have to first break down what a geometric mean is and then see how that applies to these right triangles and their altitudes. Okay, so the definition of a geometric mean says you have A, B, and G. They're positive numbers. They're going to represent side lengths, so of course they have to be positive. So G is the geometric mean of A and B if and only if this situation arises. So we've been relating similar triangles to each other with proportions and then cross multiplying. So one side compared to the same side in the other triangle equals another side compared to the same corresponding side in another triangle. So what's going to happen is we're going to have these special cases where we set up these relationships, these proportions, and we're going to have the same number or the same side represented in these two spots, where when we cross multiply, it's basically going to be, not basically, it is, it's going to be some number times itself because of that relationship. So watch what happens. If I set up my corresponding sides and I end up having the same number or the same side length represented here, when I multiply g times g, when I cross multiply, I'm going to have g squared and then a times b on this side. And then if I break that down even further, we know that to get rid of a square, we're going to go ahead and square root. And so to simplify this, g, we take the square root of g squared, we get g, is going to equal the square root of a times b. And you can see in the next box here, the geometric mean theorem states that the geometric mean of the positive numbers a and b is the square root of AB. And I just showed you how that happens. So a geometric mean happens here when we have the same side length, the same number being set up in a proportion diagonal to itself so that it's always going to be multiplied and become g squared. And then we have a and b. So when we talk about that geometric mean, that's what we're looking at here. The geometric mean of a and b is this number. So if I move down to my examples here, just real basics, find the geometric mean of 4 and 64. I'm going to go ahead and set up this relationship here and solve for the g being the geometric mean. So of 4 and 64, just like if it was a and b, 4 and 64 would go into these spots. So if I want to find the geometric mean of 4 and 64, I'm going to set it up like this, and I'm going to cross multiply. So g times g is g squared. 4 times 64 is 256, and then I'm going to square root to try and find g, which represents the geometric mean. And the square root of 256 is a nice number. We can go ahead and just plug that in. It's 16. Okay, so let's write this out so we know what we're solving for here. The geometric mean of 4 and 64 is 16. Okay, so on that first one, I went all the way back to this original proportion and cross multiplied. But when we know what the geometric mean is representing in terms of these two, we can jump directly to here. So what we could have done, I'll write this in a different color, is we could have said g equals the square root of a times b, so 4 times 64, instead of going back to the original proportion. But I wanted you to see where this is coming from. But if I went straight to this, 4 times 64 would have got me the 256, and then I would have ended up right here having to take the square root of 256. So we can write that out. G equals square root of 256, 56, which equals 16. So we can jump straight to here instead of going all the way back to the proportion, but it's good to know where this comes from, so that's why I represented it like that the first time. But when we work in these triangles, we're going to just jump straight to here. We're not going to go back to the proportion, although I'll show you where it comes from. So find the geometric mean of 5 and 45. So let's just jump straight into this form right here instead of doing the proportion. The geometric mean of 5 and 45 is equal to the square root of 5 times 45. And again, where that would come from is g times g and 5 times 45. You're going to get whatever number that is. So 5 times 45 is 225. And 225 also has a nice square root, which is not going to be the case most of the time, but we're just setting up some easy ones here. So g equals 15. So 15 is the geometric mean of 5 and 45. All right. So now let's relate this directly to the right triangles. That's where we were going, but we had to first understand what this looked like and how to solve them. So our right triangle altitude theorem, as we referred to in the big idea, has two different situations. So in every right triangle, the altitude, so here's a big right triangle. The altitude is like the height. It's going to go across. Now we're specifically going for, there's an altitude in every direction. There's an altitude this way, there's an altitude this way, there's an altitude this way. So every triangle has three heights or altitudes. We're specifically looking at the altitude that goes to the hypotenuse. So remember, you have in a right triangle, two legs, and across from the 90 is the hypotenuse. So we're specifically looking at the height that goes to the hypotenuse, the altitude to the hypotenuse, is the geometric mean of the segments into which it divides the hypotenuse, which would be x and y. So what this is saying is h would be g, is the geometric mean of x and y. So if we take a look at it right here, h is the geometric mean of x and y in this situation. If I multiply x times y and I take the square root, I get h. We'll look at why that is in a second, but first let's break down this theorem and make sure we understand these two different pieces. Number two, each leg, so B and A, you can see we're looking at those, is the geometric mean of the hypotenuse, which is the entire side here, which we'll call C, which would be x plus y, but in this case we're going to call it C. So the leg A is the geometric mean of the hypotenuse C and the segment of the hypotenuse adjacent to the leg, meaning the hypotenuse gets cut into these two pieces. We're looking at the piece that's closest to that leg. So if we're referring to A, we're looking at C times X. And if we're looking at B, we're looking at C times Y. So we're looking to the piece of the hypotenuse that's closest to or adjacent, which means next to that specific leg. So when we're looking at A, that's equal to the square root of C times X. See that here. And if we're looking at B, that's equal to the square root of the entire hypotenuse C times the adjacent piece Y. Now, when we get down to the nuts and bolts of this, you kind of just have to memorize those facts, and you practice it a couple times and you start to remember which pieces go together. But let's talk about why this works. So we've got this really big triangle, and we draw this altitude to the hypotenuse, and now we end up with three triangles. We have the original big one, and then we have this one, which I will highlight in red. And we've got this bottom one, which I'll highlight in blue. The reason all of this happens and why we're studying it in this section is because when we draw this altitude, we end up with three similar triangles. So remember, for them to be similar, one of the ways that we can prove that they're similar is to show that two angles are the same. So first of all of these are going to have a 90. So if you look at the big one, the 90 was given to us. When we draw this altitude to the hypotenuse, it automatically is going to have that 90. So this blue one has the 90 here, this red one has the 90 here. So all of them have a 90. And now if I'm comparing the big triangle to the red one, notice that they're going to share this angle. That angle is part of the big triangle, and that angle is part of the red triangle. So just looking at the red one and the big one here for a second, they both have this angle, whatever it is. Say it's 40 degrees. It's part of both triangles, and they both have a 90. 90 for the big one, 90 for the red one here. As soon as I see that they have two matching angles, I know they're similar. which means I can set up some proportions here because of it. Same thing over here. The blue one has the 90, which matches this 90 on the big triangle. And then both of them are going to share this angle. So we've got the big triangle using this angle here. And then the blue one is also using that angle there. So two equal angles means all three angles are equal. So they're similar. So their sides are in proportion. That's what we've been studying. So because of that, we can match up and set up proportions with their corresponding sides. So I'm going to try and set this up for you so you can see specifically where these come from. To actually get these problems solved, you don't necessarily need to understand where this comes from, but I want you to understand it at a higher level, so that's why we're going to go through this right here. Okay, so if we are looking at, let's relate, we got to use this h somehow. If you notice that h is the base of the red triangle, if you look at it like that, with x being the height. So if I take the height, which we'll say is x, of the red triangle, and I compare that to the height of this one. So I kind of messed it up. It's going to be the height of the blue triangle. So let's take one quick step back. I kind of overjumped things here. So we talked about how the red triangle is similar to the big triangle. The blue one is similar to the big one. Well, if they're both similar to the big triangle, that means they're also similar to each other. So we can compare them to each other, which is what we're going to do here with the base and the height of each. So in the red triangle, let's go ahead and put this 90 here. You've got the red triangle. The height there is x, and if I compare that to the height of this blue triangle, if you take a look, the blue triangle, the 90 is here, you'd have to spin it this way, but the height there is h. And then remember, we're trying to set up a geometric mean here, so we're specifically picking the sides that are going to correspond here. So now if I go back to my red one, because I'm comparing red to blue, the base of the red one is h. And if again I flip this one back this way, we called the height h this way, which means the base would be y in this case. So because they're similar, we can match up red height to blue height, red base to blue base. Cross multiply, you're going to end up with h squared equals xy, which I then would square root. And that's how we end up here with h equals the square root of xy, being the geometric mean. Now that's the information that we need, but again, I'm trying to show you where this actually comes from so we can understand it at a little bit deeper level here. So then what about these other ones? So when we start looking at A equaling C and X, notice that C is the full hypotenuse of the big triangle. A is one of the legs of the big triangle. So now we're going to relate the big triangle to the red, and then we're going to relate the big triangle to the blue, and that's going to give us these two pieces right here. So let's go back to the red one again, and let's use x as the height. We know we're going to have to go ahead and use something here twice. In this case, that's going to be the a, the geometric mean. So we're going to use a as the hypotenuse of the little triangle and the leg of the big triangle. So when we look here, x is the height of the red triangle, and if I look at the height of the big triangle, that's a. Make sure that's not a 9, that's an A. Okay, and so I looked at the red triangle compared to the big one. Now I'm going to look at the hypotenuse. Again, I want this to set up so A goes across from A. So I've got the hypotenuse to the red triangle here is A. And then the hypotenuse of the big triangle here is C. So when that gets cross multiplied here, it's A squared equals C times X. And I would square root, and then a ends up equaling the square root of c times x. And then we can do the same thing over here on the blue triangle. All right, let's just jump straight to the hypotenuse here. The hypotenuse of the blue one is b. The hypotenuse of the big one is c. All right, and then I'm trying to use b as the geometric mean here. So if I'm going to go ahead and match this up, when I'm talking about the big triangle, B is going to be a leg. Now remember the big triangle was here on the bottom, so I'm going to go ahead and put B there. So first we started talking about hypotenuse to hypotenuse. Now if I want to make sure we're talking about B here, so it's the geometric mean, That's the leg. So if I go back to that blue triangle there, my leg is going to be right here. It's going to be y. And so when I cross multiply here, I'm going to get b squared equals cy and square root. Now, that gets very complicated right there because there's tons of these different cross multiplying proportions that I could set up based on these three similar triangles. We're specifically trying to find the ones that set up this geometric mean property. If you feel like you got lost in the process of that, that's okay. We really just need to focus on these two things. So let's go back to that and then we'll reinforce it on the back. The altitude of the big triangle, the altitude that goes to the hypotenuse, is always going to be the geometric mean of these two. So h equals the square root of x times y. That comes right there. And once we do that a couple times, that'll be nice and easy. The leg is always going to be the geometric mean of the entire hypotenuse and the little piece that's adjacent to it. So a is equal to c times x under the square root. And then the other leg of the big triangle is going to be equal to the geometric mean of the hypotenuse times this y right here. So we square root that. All right, so if we kind of got lost in the weeds on all that, I apologize. But once we start plugging numbers in here, this will be real easy for you to solve. So let's take a look at the back. So example number 2 here. CD is the altitude. Okay, that's all given to us here. They gave you these numbers, 10 and 16. They want you to find these three pieces. So these are the three different pieces that we're going to look at referring back to here. One of them comes from number 1, and then we have each leg, so we have 2 situations here on number 2. These 3 different things can help us solve for these pieces. So let's start with CD. I'm going to call that x. So if we go back to our theorem, the altitude is the geometric mean of the segments in which it divides the hypotenuse. So here's the altitude. It's the geometric mean of the 2 pieces of the hypotenuse. So this is actually real straightforward, nice and easy. X is the geometric mean of, meaning we're going to square root of this times this, 10 times 16. So x equals, now in this case, we're going to try and leave this in simplest radical form. Because I see that 16 already separated, I'm going to remember that here. I'll go ahead and multiply so we can see what this would look like in a normal problem. But in general, you could go ahead and split this right now. We're going to leave this in simplest radical form. So when I go back to simplify square root of 160, I want that 16 separate. Because when you go ahead and take the square root of 160, you should always check and see, is that a nice number? It's not. So we're going to put this in simplest radical form. So square root of 16 is 4. Nothing happens with the radical 10. So that's fully simplified there. If they wanted this rounded, and again, we're solving for CD here, we would go ahead and just plug in 4 radical 10 into our calculator. Or we actually could have just plugged in the square root of 160 back then. There was no reason to simplify it if they just wanted it rounded. So it would be 12.65. And we'll put the squiggle because we rounded it. All right, so the altitude is always going to be the geometric mean of these two, and that's how you set it up. The 2 pieces being multiplied underneath the square root. Now let's do one of these legs. So let's do CA. I'm going to call this Y. So y is going to equal, y is the geometric mean, meaning you multiply and take the square root of the full hypotenuse times the adjacent piece. So the adjacent piece is 10. And the full hypotenuse here would be all of this. So the 10 and the 16 together is 26. Okay, so I'm going to go ahead and multiply that. That's 260. And we need to simplify that. Don't see a lot of good numbers that go into 260. You could try 16, doesn't work. You could try 36, doesn't work. But if I do try the simplest of all my perfect squares, 4, it goes in exactly 65 times, which can't be broken down. So we're going to have a 4 and a 65. The 4 becomes a 2. So 2 radical 65 is what we're looking at here. If I went ahead and got the decimal version and rounded that out, it comes out to approximately 16.12. Okay, and then the last one, I'm not going to call it Z because my handwriting's bad and it ends up looking like a 2. So I just picked a random letter. I'm going to call this E. You could use any letter you want. So I'm going to say E equals, okay, and it's going to be the square root, again, of the whole hypotenuse, but now times the other adjacent piece, 16. So it's going to be 16 times 26. So when we're solving for these legs, it's the whole hypotenuse and the piece that's close to it. If we're solving for the altitude, it's just the two separate pieces. And again, once we've done that a couple times, it's kind of easy. It's the same thing every time. You'll just memorize that. So 16 times 26. I'm not going to go ahead and multiply that because I see the 16. I'm just going to go ahead and keep these separate right now instead of breaking it back up after I've multiplied them. I know the square root of 16 is going to be 4. And 26 cannot be broken into anything that has a square root. So that is fully simplified. And so CB, if I went ahead and got the decimal version here, it comes out to approximately 20.4. All right, the additional example here is exactly the same. If you're watching the video, I would recommend you pause it, try it, and then see how you did. Okay, so I'm going to go ahead and start with the altitude here, which again comes from these two pieces, the geometric mean of those two. So x is going to equal the square root of 18 times 12. Okay, 18 times 12 comes out to 216. And if I take the square root of 216, it's not a nice number. So I need to start looking for things that go into 216. 4 works, but with 54, I'm going to have more work to go. So 216, let's see if something better works. 16 doesn't. How about 36? Sure does. How about 64? Does not. So try your perfect squares. The larger the perfect square you get, the easier your life is going to be. If you keep using 4 every single time, you're going to have to simplify multiple times. We've talked about that before. So 36 and 6 is going to work out nicely for us here. 36 and 6. The reason is square root of 36 is the whole number 6, and then we still have square root of 6. That's fully simplified. That was NP. And if I rounded that to the nearest decimal, it's going to be 14.7. All right, so that's solving for the altitude. Now let's go ahead and solve for each one of these. For ON, I'm going to call that Y. Y is going to equal square root of the entire hypotenuse, which in this case, 18 plus 12 is 30, times the piece that's next to it. So it's going to be the 12 that's next to it times the whole hypotenuse, which is 30. I go ahead and multiply those together. 12 times 30 is 360. Okay, and then the square root of 360, not a perfect number, but I see that 36 inside of it, times 10. So I'm going to go ahead and break that into 36 and 10. So I get 6 radical 10. That was NO, and that comes out to approximately 18.97. All right, and then the last one, we'll call this E out here. That's going to be equal to square root of the 18, the piece next to it, times the whole thing, which is 30. Go ahead and multiply that through. I get 540. So now when I want to simplify 540, 4 works, but I still got that really big number. Let's see if there's something better. 16 does not work. How about 36? Sure does. And 15 is not going to be simplified anymore. So I'm going to go ahead and stop right there. 36 and 15. 36 again becomes a 6. Radical 15 can't be simplified, so we leave it just like that. So MN equals approximately 23.24. All right, one more challenge question that they like to relate this to. If we take a look inside of a circle, we've got this drawn. They told you that this is a semicircle, so it's exactly half a circle. This would be the diameter of the circle if you extended the full circle. All right, that's the diameter across. They want you to actually find that length here. So find the diameter of the semicircle at the right if AP is 5, BP is 10, and they tell you that BP is perpendicular to PA. So what that means is we can create one of these special triangles and use the geometric mean to solve it. So here's what it's going to look like. I can go ahead and draw a line between A and B, and then draw a line from B to C. And I've created one of these right triangles. Now, how do I know that this is right? Well, we've studied that these angles that are coming from the side of a circle, they project out to a certain degree measure, right? And they are half the size. So if this is projecting out to half of the circle, which would be 180 degrees, this is half the size. So I automatically know that this is 90 in this case. So when I have an angle that projects to a diameter, it's automatically 90 degrees. So we needed that information just to create another one of these triangles. We have a right triangle, we have an altitude. We can go ahead and relate these geometric means. Sorry about that announcement there. All right, so I'm going to relate this 10, which is the height, to these two pieces. So the height is the geometric mean of these two pieces. So let's call this x. So I know that 10 is equal to the square root of this times this, 5 times x. And if I want to go ahead and solve this, I actually want to get rid of this square root so I can start moving things around. So just like if I want to get rid of a squared, I take the square root. If I want to get rid of a square root, I square both sides. So I'm going to square this side and I'm going to square this side, and it reverses everything. So 10 squared is 100. And when I square a square root, they just cancel each other out and it goes away. And so I have just 5x. Well, that's pretty simple to solve at that point. Just divide by 5. All right, and 20 equals x. So this piece right here equals 20. And then we always want to make sure, yes, we've done some great math here to figure that out. But what we haven't done is actually answered the question. So it says find the diameter, which would be AC. So AC, the full diameter, is going to come from AP plus PC, which is 5 for AP, and then the 20 that we just found. And so AC, the diameter, is 25 total. So this whole diameter is 25. So just an example of how we can create one of these special situations with a right triangle and an altitude, and we now know that we can use the geometric mean to find those missing pieces.